introduce today's speaker. It will be Codina Cotar from University College London, and Codina will will tell us about equality of the next order terms for the Jellium and uniform electron gas for Coulomb and Riesz potentials. So Codina, please take it from here.
Thank you very much. Thank you very much for inviting me to talk here. It's really a great pleasure to do so. So I'm going to talk about some models. So some models are coming from optimal transport. So this uniform electron gas, and the Jellium is connected to point configurations. So I will first give a bit of motivation about why one should care about the optimal transport problem. And then I will explain how it connects to two other models, so to this Jellium model and to the Coulomb and Riesz gases. And I will talk about some new work. Well, it's not so new. It's actually probably 1.5 years old, but I was very sick for 2 years. So, but it didn't get put on archive, but it will in a couple of weeks. And some of the work I will talk about is a bit older. Okay, so, all right, so the motivation. So the motivation for the optimal transport problem comes from quantum mechanics and so-called density functional theory, which is shortened to DFT. So basically, if we look in nature, what we have all around us are material systems which have electrons and nuclear charge, and all the properties that we see the systems to have, such as mechanical, electronic, magnetic, they are due to the electrons and to the way they interact with all the other electrons in the system. And the way physicists define this interaction is via Schrödinger's equation. And this Schrödinger equation can predict lots of things, such as binding energies, equilibrium geometries, intermolecular forces. Now, mathematically, the Schrödinger equation is expressed via a PDE, which has such a form, and we call this PDE a Schrödinger equation. And it's a PDE for a function psi, which for simplicity, I would say it lives in R to 3n, but it's actually more complicated. It's complex, and it also depends on the spins on the electrons. However, I'm not going to complicate things here, and I'm just going to say that it depends on R to 3n. So if we were able to solve this equation explicitly, then we'd know a huge amount more about the systems around us than we do. However, we do not. Yeah? Now, in physics, the solution of this PDE, the psi, is called the wave function. And it represents the state of the n particle system. So where n here is number of electrons, and the xi's are where the electrons are situated in the system. Now, psi has a very nice probabilistic interpretation, and it's nice because it allows us to call upon some probability tools in order to try and say something more about the mathematical problem. And the way it connects to probability theory is as follows. So if I take the absolute value of this psi and I square it, then this will become a density function. And it's the probability density that electron I is at position xi. Now, one nice property that psi has is that it's an antisymmetric function. Yeah? So if I swap if I swap the psi for two directions for xi and xj, then it becomes minus the psi for the swapped two positions. So because it's antisymmetric, this makes the density a symmetric probability measure. And in probabilistic terms, it's called unexchangeable, and it leads to some cool properties like an extendability and the Finetti theorem, and these are lots of nice cool properties that help us. Now, what we would like to do, we would like to solve the many electron Schrödinger equation. And if we could do that, pretty much almost any property of the materials could be determined accurately. However, we cannot solve it. So what physicists have come to do, so they have created something called density functional theory, which is an approximation or trying to approximate the solution to this to the Schrödinger equation. However, you run into the curse of dimensionality. And the curse of dimensionality comes at quite small electron values. So for example, if I take the carbon that has n electrons. And what will appear in the Schrodinger equation will appear will appear r to power. So you will have to discretize r, and remember you have r to 3d to 3n, so that will lead to r to 18. And if I discretize, for example, just by 10 points, I end up to 10 to 18 grid points in my approximation. That's not feasible. Also, a lot of my systems will have millions of electrons, so approximations are not so good if I try to do it this way. So what physicists have done, they've come up with this DFT, density functional theory. And what they're trying to do, so they are saying, well, I don't want to use this psi. I don't want to use the psi. It lives on R to 3n. It's a very big space. I don't want to work with it. I want to work with something simpler. And what we're trying to work with is something called single electron density, which is basically what we get if we integrate in the psi density, if we integrate all the positions apart from one of them. It doesn't matter which one of them we integrate, because this absolute value of psi is symmetric. So I can integrate x2 to xn, and then I'm left with a nice density which lives on r to power on R3. Yeah? So that's much nicer. So what we want to do, we want to find approximations of the solution which only involve this single electron density rho. And this is something we want to do for many of our systems. And as I said, many of our systems will have certainly more than 12 electrons. So many of them will have lots of electrons. Now, before I go a bit more rigorous, just a bit of history of DFT. So the first simple model was introduced by Thomas Fermi in the 1920s. Basically, they introduced a really simple system in which all particles were independent. So that would lead us to the product measure. And I will come back to that in a bit. Then in the 60s, Hornberg, Kohn, and Sham, they came up with a practical method based on what they call semi-empirical functions of rho. Basically, they are trying to approximate the solution by functions of which depend on rho. Mathematically, such a method was justified later by Levy and Lieb. And they also reformulated the Schrodinger equation is something which looked a bit better, but still was not possible to solve it. And once DFT was introduced, it became very popular. Well, it was not accurate at first. It actually didn't start becoming accurate in the 1990s, when it was an explosion of DFT in quantum chemistry. And this was because computationally things became a lot easier to work with. And this led to the discovery of many semi-empirical functions. So there's many of them. So if you Google semi-empirical functions of rho, you will end up with many such functions, some of them which depend on lots of terms of rho. I will give you two very simple ones in a bit, but there's many of them, and some of them have many terms. Okay, as a fun fact, before I become a bit more rigorous, there's more than 15,000 papers per year which use the keyword density functional theory. And my favorite fun fact is that the most cited physicist of all times is actually not Albert Einstein, but a designer of DFT models, and it is John Perdier. And he has almost 3 times as many citations as Einstein as of this morning. Okay, so let's turn this a bit more into math. So the key quantum mechanics quantity that we care about is the so-called ground state energy. So this is the state of lowest energy in a system. And you write it, you have the energy, which is a function E of the wave function psi, and you take infimum after all the psi of all the psis which have the nice antisymmetric property. And this energy E of psi is in its term formed of 3 terms. So you have T, which is a kinetic energy, VEE, which encodes the interaction of electrons with each other, and the VNE, which encodes the interaction of the electrons with a nucleus. Now, VNE is a nice quantity and it doesn't bother us when we take the infimum. However, the kinetic energy and the electron-electron interaction cause a lot of problems. In some sense, we could think of these terms, their expectations with respect to the symmetric probability density, which is the of size of about psi on R⁻². Yeah? So you can think of them as expectations. And we want to minimize this quantity. Now, a priori, this is a really unpleasant formula, and this was reformulated non-rigorously by Hornbeck, Kohn, and Sham in the 60s, and then by Levy and Lieb later on. And the way they tried to reformulate it, they wanted to try and reformulate it in terms of the single electron density, but it wasn't actually possible to just write it in terms of the single electron density. They had to use also the so-called pair electron density. So the way any two electrons interact with each other. And this is basically, so if I take the absolute value of psi and I integrate any n-2 of them, this will give me ρ2. Okay, and with this in mind, we can rewrite this infimum in something which looks slightly more appealing mathematically. So this is how we reformulate it. So we define it as a double minimization. So the first one is after all the ρ, which are the density of some wave function. And then the second minimization is after all the wave functions which have a given ρ as the marginal. And with this double minimization, we have infimum after ρ of hk, so this is called the Hornbeck-Kohn functional, plus n and this integral. Now this one is what comes out of the VNE, so electron-nuclei interaction. So this is why I said it's a nice term, because when I do some formula manipulation with it, it ends up just with an integral depending on the single electron interaction. So it's a nice quantity. The not so nice quantity is this Hornbeck-Kohn functional, which has in it both the kinetic energy and the electron-electron interaction. This is a very famous quantity, and it's called the Hornbeck-Kohn functional. Now, if we look at this new formulation, it looks prettier than the original infimum minimization after 3 terms. However, it's not really simpler to work with because I'm still taking infimum after the psi. So I still have to deal with a very large R⁻³ space. It's just something which looks a bit better visually. And the second reason it's helpful is because it allows us to start devising approximations. So the way the approximations work, so we try to devise approximation to this Hornbeck-Kohn functionals. Okay, so what do we have? We have to minimize an energy functional, which depends on the single electron density. However, as we've seen here, it also depends on the large space. And if we work a bit more, and if we play a bit more with this formula, it will depend on this ρ2, on the way any 2 electrons interact in the system. So that means it depends on the correlations in the system. And what density functional theory models do, they try to guess what ρ2 is in terms of ρ. And the standard way that people work within DFT is start by saying all particles are independent. And after that, they try to add corrections based on the fact that all particles are actually not independent. And it can lead to to accuracy, but it's not always accurate. It depends on the system. And I'm going to just mention top 2 popular density functionals. So the first one is the Thomas Fermi one, the mean field approximation. So this is everything is independent. And when everything is independent, I just end up with a product measure. So I can approximate the electron-electron interaction by the product measure, and that allows me to work with something nicer when I come to the Horn-Bacon functional. Of course, all particles are not independent, so this is not something we can do. So then we add corrections. So they will say, well, it's not the mean field, but it is the mean field plus something else. And the next one that people developed was the local density approximation. So this was mean field and add some terms, which looks quite mysterious at first. And the first time they added was you had this integral of x to power 4 over 3, and then you had the number n to power 4 over 3 and some term here. So this was the first term they did. Then later on, it turned out that actually these two are the first two terms if I want to have a good approximation of the Horn-Bacon functional. What is not good is the constant that comes in here. And I will come back to this later on in my talk. Okay. So this is what physicists have done. And actually, if you Google these density functional approximations, you will see that there are a lot of these functionals, and some of them have many terms. Some of them have over 40 terms. So they will start with J, then they will add this term, and then they will add lots and lots of other terms depending on various powers of rho and of n. And they look mysterious at first, but and I'm not going to go into that. What I'm going to try and do, I'm going to justify these first two terms, and then I will connect to the Jellium problem, and I will also connect to the Coulomb and Riesz gases problems. Okay, so the way this started for me, so I was very interested in physics applications, and when I was in Munich, I started discussing with Gerhard Frieseke, and then it turned out we could use optimal transport to say something more about the Horn-Bacon functional. And what we could say about it, so if we go back to the Horn-Bacon functional, that if we take this h to 0, so h is the small Planck's constant, and it appears in a precise form in the kinetic energy. And what happens is that if you take this h to 0, it turns out that the limit you get will turn out to be a many-marginals optimal transport problem. More precisely, it will become this problem. Yeah, so it will become this particular problem. So that you have probability measures gamma n, which are symmetric, and they all have marginal mu, with the density rho being the single electron density, and you have this particular Coulomb cost coming into play, and you're going to take the minimization of all this gamma n. And why is this helpful? Well, if I wanted to devise a Taylor expansion for the Horn-Bacon functional, this means that the first term in this expansion is a many-marginals optimal transport problem, yeah, corresponding to n marginals, n equal marginals, all having marginal density rho. And this was the starting point. Nowadays, you can do a bit more. So if the first 10 is this optimal transport problem, you can also say nowadays something about what is the next term in this expansion. But I'm not going to go into this. I will go into trying to connect it to the point configurations problems. Okay, just briefly, many marginals optimal transport problems. So you have a measure in R to ND. You have some marginal measures mu1, mu2 to mu_n. You have something called the cost function, which is just a function living onto R to ND and takes value in R or infinity. And what we want to do, we want to transport mass from a given pile ρ1 or mu1 into a number of given holes, mu2, mu3 to mu_n. And we want to minimize the transportation cost subject to having the fixed marginals mu1 to mu_n. And in optimal transport, there's a number of questions people care about. So they want to know, is there a solution? So do we have a minimizing gamma? Then if you are able to find a minimizing gamma, you want to ask yourself whether this minimizing gamma is unique, if it has some other properties such as geometric properties, and so on. And this is the kind of question you can also ask yourself regarding this optimal transport problem. If you have two marginals, which corresponds to the physically not exciting case with n2 electrons, then we can answer a lot of these questions. For a larger number of electrons, there's various works which have been done in the literature, and I'm not going to go into it. I'm going to go straight into the let's take number of electrons really large, which is the one that is is realistic if you have a system with many electrons. Now, for the rest of my talk, I'm going to use this in the notation FNC or T of mu. So this is, I have an optimal transport problem with n marginals. And for me, I'm going to take all marginals equal to mu, just because of the interest to the physics problems. Though of course you can also some of the results may adapt also to the case when we have different marginals. And I'm going to take gamma to be symmetric, though it actually you don't have to take gamma symmetric, because you can start with a problem where you take the minimization after all gamma, and then you can show that it is equal to the one where you just take the minimization of the symmetric measures. So it just brings some nicer properties to work with. And the case that comes up from the physics problem, so was the one with 1 over norm of x minus y. So this was the three-dimensional Coulomb. And in general, it doesn't cost that a lot more to actually look at the more general risk case, where I, instead of 1 over norm of x minus y, I just look at 1 over norm of x minus y to power s, where s is between 0 and d. And for this case, I'm going to use the notation f n s or t mu. Okay, so let's see what kind of result we can get in this case. So the first thing you want to do, you're going to look at something called mean field function. So I'm just going to basically divide this quantity by n squared. And it turns out it has a limit, and it is the so-called mean field function. And if we remember way back when I was telling you about the physics approximation, it is exactly the J. So it is exactly the mean field approximation. This is the first term. So you end up with a mean field approximation. And the way we do this proof is by using probability tools such as definitive theorem. So we use exchangeability, and we end up with this limit. Okay, so then the next thing we care about is the next order term. And the next order term takes us to something which in physics is called exchange correlation energy. An exchange correlation energy is equivalent to looking at the optimal transport problem minus the mean field term. So this whole thing is called exchange correlation energy, and I'm going to call it ENSXC from exchange correlation. And there is a very famous bound in mathematics, which is called the Lieb-Oxford bound, which was shown way back, but I think more than 40 years ago, maybe in early 80s. So there's a number of papers started at the end of the 70s by Lieb and Oxford. And then they showed that if I look at the exchange correlation energy and I divide by n to 1 plus s over d, this turns out to have a lower bound, and it looks of this type. And then there's a lot over the years, there have been a lot of papers where they try to refine this constant CLO. So they call all the constants which they put in front of this integral they call them Lieb-Oxford constants. And there have been many papers. So if you Google Lieb-Oxford bound or Lieb-Oxford constant, you will see there's hundreds of thousands of citations, and there's many attempts to try and find which is the optimal constant that we should put in here. And why do we care about that? Well, we care about that because that is what we should put here. So it should be the integral times the optimal Lieb-Oxford constant. So this should be the next term in the many expansions that we derive. Okay, I will come back to the Lieb-Oxford constant in a bit. Now, trivially, we also have that this exchange correlation energy is bounded from above by zero. That is because I can, for example, take the product measure as a competitor in the optimal transport problem, and then I will get zero as upper bound immediately. So then once I have a lower bound and an upper bound, there's a natural question for us to ask, well, is this limit, does it exist? So can I say anything about this limit? Does it exist? And if it exists, what kind of properties does it have? And well, there have been a number of people who've worked on it. So the first one was Di Marino. He looked at the D equal 1, so the one-dimensional case. And he looked at the Coulomb and viscous, so 1 over num of x to power s. And dimension 1 is actually quite special in optimal transport. So usually it's a lot easier to find explicit solutions for dimension 1. Once you go to dimension 2, things become a lot more complicated. But in dimension 1, it's quite simpler generally. And this simplicity allowed Simone Di Marino to find explicitly, to show explicitly that the limit exists, and he actually could calculate what the limit was. Then in the same year, just a few months later, there was a paper of Lewin, Lieb, and Seiwiger, and they used something called Graf-Schenker decomposition to show that a limit does exist. So they looked at measures mu, which have density rho satisfying this property. So they are continuous and they are slow varying densities. Then just the same year, Micha, Petrak, and myself, so we generalized these results to any S between 0 and D and any D. And for us, the rho is quite general. And we use something called Pfefferman-Gregg decomposition and also optimal transport tools. And what all these three results, so if I put all the results that everybody in 2017 got, so what we could say is that we can show that the limit of this quantity is, and it is equal to some constant, which only depends on S and D. And then you have this integral of rho to 1 plus S over D x dx. Now I'm calling this constant CUEG from the case where rho is a uniform measure. So the case where rho is a uniform measure has a special name in the physics literature. It's called uniform electron gas. And it goes back all the way to Dirac. And for this uniform electron gas, so there have been a lot of papers over the years where people were looking at, so in the relevant dimension 3 and for the Coulomb cost, so they were trying to say things about this exchange correlation energy. And they even conjectured for a long time what this constant should be. So the conjecture was that is 1.4442, but this hasn't been proved. So before I move on to the other models I will talk about, I will briefly tell you about this Pfefferman-Gregg decomposition that we worked with. So this was introduced by Pfefferman for Coulomb in dimension 3. Then a PhD student of his, Craig, extended it to any dimension and to S having these values. And then Micha and I extended it in 2019 to all S between 0 and D. And what does this Pfefferman graph decomposition do? Well, we start with 1 over x minus y to d, and norm of x minus y to d. And this is a long-range interaction. And well, long-range interactions are tricky for the optimal transport problem and for other types of problems too. And for a lot of problems in lots of areas, actually a lot of problems in mathematical physics, long-range interactions are tricky. And we don't want to work with a long-range interaction problem. We want to turn it into a short-range interaction problem. So this is what we do. So we can transform it into a short-range interaction problem by showing, so and we have to pay a price. So how do we turn it into a short-range interaction problem? So we have a family of ball packings of various radii. So the smallest one is R1, and we have M different radii, R1, R2 to Rm, where Rm is the biggest radius among them. And we can write a probability measure. And in this way, what we are going to end up, instead of 1 or a norm of x1 minus x2 to power s, we end up with these new costs, which are given here in this integral. And now if we look, we no longer have a long-range interaction. We have only interactions x1 and x2 in the ball A. So we have a short-range interaction. Of course, we have to pay a price, and this price is paid by W, which is an error, and basically it takes everything else. So it's 1 of a norm of x1 minus x2 minus my short-range interaction, and I'm going to call that W. And well, why is it useful? So well, we can show that W has nice enough properties. So first is positive definite, and secondly, if I were to define an optimal transport for it, so if I were to define this optimal transport for it with W instead of C, then if I were to divide it by n to power 1 plus s over d, and I were to use m, the number of balls, to have a relatively large number of balls, then this W, the optimal transport corresponding to this W vanishes. It goes to 0. So for large enough n and large enough number of balls, this will disappear. So you can say that in the large n limit, I have the original long-range interaction optimal transport problem is equal to 1 for a short-range interaction. So it is very useful, because once I work with this short-range interaction, then well, it turns out to be easier to show the next order term. So it turns out to, so basically what we do, we show that the optimal transport problem for the original long-range interaction is equal to the one for the short-range interaction. And then we show that for the short-range interaction, the limit looks like this. So basically, this is how we solve the problem. So this was the problem that we originally started with. So looking at the problem, and it turns out that we can take this Pfefferman-Gregg decomposition and we can move it to other problems of interest. So we can take it to the so-called Jellium problem, and also we can take it to the Coulomb and Rhys gases problem that Stefati and collaborators have worked on. Now, one other thing I want to say before I move on is that these short-range decompositions have been, various types of short-range decompositions have been studied quite a lot in mathematical physics. So there's people like David Bridges and Roland Bauer-Smith and collaborators, and they've worked with other types of short-range decompositions. So they work with them for something called the 5-4 model and other types of models that appear in mathematical physics. So there's a lot of other decompositions that people can use. Basically, the principle is always the same. You have something which is a long-range interaction, and you try to transform it into a short-range interaction, and you have to pay some price via some error. However, you'll usually be able to do it because the error will be something positive, definite, and it will be controllable in the long run. Okay, so once we have the next order term, you can ask yourself other questions. You can try to ask yourself the speed of convergence. So how fast is this, say, this convergence that we have? And we called it small oscillations result. And at the time, we did this first paper, we couldn't get it exactly for the optimal transport problem. We got it for something which called grand canonical optimal transport. So it's a convex hull. But nowadays we can actually get it for the original optimal transport problem. So basically, suppose I take any n and n tilde, and I look at these respective. So I take exchange correlation energy, I divide it by the corresponding n to 1 plus s over d, and I look at the difference, and I want to know how this behaves. And we can get a bound, and we have a nice bound which doesn't in fact depend on s, so it's nice and uniform in s. Now, if you are interested, for example, just in the Coulomb case, so if you take s equal, it's just dimension 3 Coulomb case, then you can get a better bound. Yeah, and you can also get a better bound if you look at the Coulomb in a general dimension. But if you try to get such a speed of convergence for all s, then you get a slightly worse bound. Now you may want to ask me, why would you care about getting this bound? Well, it will give rise to lots of other cool properties. I think I don't have time, so I'm going to skip the grand canonical optimal transport problem. But basically, what you end up as a consequence of these small oscillations is you end up, for example, with some nice uniform convergence. So for example, if I define Fs of n, the exchange correlation energy divided by n to 1 plus s over d, this converges uniformly with respect to the parameter s. And if I have time at the end of the talk, I will come back as to why this is a nice, cool result that we can use. Okay. So let me briefly move to the other two models. So there's two other models to talk about, the Gellium model. So you have n electrons and a neutralizing background in the domain omega, which has size n. And I'm gonna minimize over the xi in omega. So I have another minimization problem. And if we think of the minimization to build Gellium, I'm going to call it gel ns omega. Then you can try to find again the limit. Yes, so the limit of this minimization problem. So this was studied in the 1975 by Lieb and Manhofer. So they showed that this limit exists, and I'm going to call it C gel of S and E. So this limit exists. Then in a version of our paper in 2019, we extended this result to S between D-2 and D. Well, it's not explicit in our paper. Basically, what we did in our paper, we showed a subadditivity result for this Gellium energy. And from the subadditivity result, and once you have a subadditivity result, you can go to the limit by a standard statistical mechanics tools. Yes, so we didn't explicitly say that the limit exists, but we did have the tools to allow us to say that the limit exists. Now, in the paper of Lieberman and Hofer, so they minimize over xi in omega. However, you can show that the minimization over xi in omega, so you can get rid of just minimizing over xi in omega. You can minimize over all xi. The two minimization problems are the same. So you can show that for s between d minus 2 and d, the minimizer sits in omega, even if you, or a priori, you minimize over all possible xi. Now this problem, so you can rewrite it slightly. So you can do a generalization of this problem. So you can take any probability measure mu and any density rho. So I'm going to take it with compact support just because it simplifies some technical questions, and you can minimize over all xi in RD. So here I've slightly changed the minimization. So before, just in some sense reduced. So here I was working with an omega of size n. Here I'm working with the support of the measure mu. So it's no longer of size n, but I'm inheriting some n factors in front of the integrals. And you can basically pass between this problem and the other problem by a factor n to s over d. So you can pass between them. It's not a big difference. And again, you can give a name to this minimization problem, is gel n s mu, and you can try to understand what its limit is. And it turns out that if you divide by n to 1 plus s over d, there's a constant which only depends on s and d, and then an integral which looks exactly like the integral we had in the optimal transport problem. Yeah, and this is something that Micha and I have proved in our paper. Then you can do, we've done this for all s between 0 and d. Okay, a couple of other little facts. So if you look at the Jellium problem, it's a lower bound for the optimal transport problem. And then the question comes whether there's any direct connection between these two. And in 2015, Lewin and Ib did a comparison for the case where mu was the uniform measure. So this was the, as I said, the uniform electron gas for the optimal transport problem. And then they tried to compare these two problems, and the heuristics were suggesting that, well, the constant that comes in the Jellium problem, the C gel, is different from the CUEG. And this, so they have heuristics, they have, but they didn't have a proof there. However, the heuristics were questioning the physics conjecture, and the physics conjectures for many years have been that the two constants have to be equal. Okay, then briefly, just before I come back to the problem of these constants, so you have this minimum energy point configuration, which is the Coulomb and Rees gases problem. So here you have the sum of 1 over norm of xi minus xj to power s plus n sum of vi, where v is a confining potential, and where the case with s between 0 and d corresponds to the Rees gas, as is the integrable kernel. And this has been quite widely studied. So there's a lot of wonderful papers in the areas, and probably the audience knows a lot more about it than I do. But there's some, I'm just going to focus on the results which are relevant to the optimal transport problem. So the second order asymptotics for S between d minus 2 and d. So they were first by Sandia Sefati, then by Gujaria Sefati, and then Mircha with Sefati, which did all the other cases plus the Rees cases between d minus 2 and d. And very easily in our recent papers, so what we did, we are able to show, using our Pfefferman grid decomposition, we can show all the previous cases plus the S between 0 and d minus 2. And basically, our approach is just the fact that we can turn a long range decomposition into a short range decomposition. So there's a lot of technical details, so it's not as easy as I'm saying, but I am going to skip this for the talk. And basically, you can want what you have for S between 0 and D. So you have the mean field case, and then you have the next order case, which takes a just similar term as in the Gellium and in the optimal transport problem, and a constant, which I have called C gas. So then I have three constants, C UEG, C Gellium, and C gas from three problems. And then the question comes, well, are these constants the same or are they different? Of course, if I look at finite n, you have three different minimization problems. However, when n takes to infinity, if we are to believe the physicist's conjecture, then this, at least the Gellium and the optimal transport problem constants, they should be equal. Yeah, and this is something that Mitja and I tried to look at. So what we were able to show, so one easy thing you can show is that you have optimal transport problem. So if for any finite and the optimal transport problem is the bigger one, then you have the Coulomb and Riesz gases one, and then you have the Gellium one. So the Coulomb and Riesz gases is sandwiched between Gellium and between the optimal transport one. Okay, and what we showed in the beginning, we just showed that the constants for S between D minus 2 and D, we showed that the constants were the same. The three constants were the same. And then in 2019, we extended it to the constants being equal for D minus 2 also. Then a few months later, after us, there was a paper by Lewin, Lieb, and Saariger. So they used the same strategy as we did in 2017, but they had a better constant. Then in 2020, we showed that the constants are actually equal for all S between 0 and D. And I should say, in fact, that also when it comes to the next order problems, we only show the next order problems for the optimal transport and for the Gellium. For the Coulomb and Riesz gases, we can also show it by our method, but we don't have to because it's sandwiched between the two. Our method would allow us to show it directly, but we basically get it for free, so to speak. Okay. So another thing that we can get just using our tools. So remember, I showed you long ago, I showed you that small oscillation. So I showed you the small oscillation theorem, and I told you that a consequence of it was that we had this sequence converged uniformly with respect to S. And well, one first step where this comes in useful is that it allows us to show that the CUEG is continuous as a function of S, and also the limit when S goes to 0 is -1. But we can actually use the small oscillation quite a lot more. So it helps us to show the next order term for the logarithm in any dimension, both for the optimal transport and for the Gellium. And it allows us to show, to look at how the derivatives of this CUEG behave with respect to some quantities, and it allows us to directly connect the constant for S with a constant for the log. So there's a lot of other nice things that one can do using the small oscillation. And the proof of this continuity is basically we just works by interchanging the limit of S and N and using the small oscillation. Now I don't have much time. I'm just going to tell you very briefly about the main step of the proof that we used for the Riesz cost. So basically the main idea that we had, so we had two problems. We had the optimal transport problem and we had the Jellium problem. And what we tried to do, we tried to construct from the Jellium minimizers, we tried to construct a good competitor for the optimal transport problem. So we try to construct a good gamma for the optimal transport. And first, in order to do this, we reduce the Jellium minimization problem to the Jellium problem with minimization of a periodic configurations. And once we did that, we used the minimizer of this periodic problem. We used it to construct a competitor to the optimal transport problem. Things are a bit more complicated because you don't end up constructing a minimizer for the per correct problem with the correct marginal mu. The marginal is slightly different, so then you have to get back to the marginal mu. But in the long run, with a bit of work, it works, and somehow this allows to show that the Jellium problem, that the limit in the Jellium problem is an upper bound for the limit of the optimal transport problem. So this is how you can do it. And to pass to the S equal D minus 2, the way we did it, we used the subadditivity, and basically we had continuity of the G problem, and we had to basically show that the C gel was continuous at D minus 2. Now for S smaller than D minus 2, we have a much simpler and a more robust way, so to speak, and it goes through looking at the Jellium problem and the optimal transport problem for the short range configuration that comes out of the Pfefferman-Gregg decomposition. So it goes through looking basically at the optimal transport problem with this cost and at the Jellium problem with this potential. And we look at them and we can compare them and show that somehow in the larger limit that they are the same, and then we can go back and to the original long range problems because, as I've already said earlier on, in the limit, the optimal transport limit for the long range problem is equal to the limit for the short range problem, and the same thing will hold for the Jellium problems and for the Coulomb and Riesz-Cousins problems. So in the limit, it's the same thing if you work with a long range on the short range problem. So then you might just as well work with a short range problem because it's nicer to work with it. Okay, so I think I will stop here, and I think I will not tell you anything else. Okay, so I will stop here. Thank you.
Great, thank you very much. This is really nice. So I'm sure there are a lot of questions, especially about the last part, about energy interactions. So please, what are the questions for a speaker?
Hi there, perhaps let me start with a simple one. So thank you for the nice talk. So one of the last slides, you were comparing these constants and you showed essentially that in all the range of S, so between 0 and D, these constants were equal.
Yeah.
But I remember vaguely that some slides at the beginning, you showed actually that some two constants were not equal, even though the physicists conjectured it.
No, the physicists conjectured that they were equal. Then there was a paper by Lewin and Lieb where basically they had some heuristics that maybe they are not equal, but the reason was that the competitor they didn't use a good enough competitor somehow in some sense. and based on the competitor they chose, it looked like maybe they are not equal. But
I got you. But so you have proven they're actually equal, and that's up to the question.
yeah, and this will go also. This should go also for the log. Yeah, which the constants are equal. I mean, I don't know what happens if you look at s greater than 0, but we haven't looked at it. But between 0 and d, the constants are equal. Yeah.
So for s bigger than d, just to.
I don't know. Yeah, I don't know what happens there. Yeah, yeah. I cannot answer anything. We haven't actually thought about it, and
Yeah.
I don't know. I wouldn't be able to give you any conjecture about what happens there.
All good. Thanks a lot.
Yeah.
Carlos?
Hi, thank you for the talk. So maybe my understanding is not so fine as to be very precise, but here is a question. So there is this argument by Lauritz where he proves a lower bound for the log energy in the sphere. He does so by studying the Gillium energy in the plane and then using this argument by Serfati, Betterman, etc. And he proves the best known lower bound for the logarithmic energy in the sphere with that. So I was wondering, would your result produce new lower bounds or upper bounds or exact asymptotics for the energy points in the sphere? Do you know about that? Or?
So we haven't yet thought of the sphere, but what I can tell you is that we think we might be able to extend. So our Pfefferman, so we use this Pfefferman-Gregg decomposition. Yeah, so basically we start with long range and we reduce to short range interaction. And even we don't work on the sphere or on any minor manifolds in general, but some we think, I mean, some of the other short range decompositions that people have worked with, like for example, David Bridges or Bauer-Schmidt, it is possible to extend some of them to manifolds. And we think we might be able, with some work, to extend ours to manifold, in which case, well, I don't know, there's a hope that maybe we could use that to say something about next order terms on the sphere. But this step, it's just speculation.
Great.
Because we haven't done it, but there is a hope.
Okay, great, thank you.
What about a hard wall confinement, like for a full dimensional set, hard wall confinement? Would that be easier? Would that be something that you could handle?
I have to say, to my shame, I don't know what a hard wall confinement is.
Well, I mean, just let's say instead of confining points to a manifold, confine them to a full dimensional set. Ball, okay, unit radius ball in RD is your confinement. So no external field. That's your.
I mean, I don't know. All I say is that Pfefferman-Gregg would work. So if Pfefferman-Gregg's, I don't know if you can do. Basically, I don't know if you can. I haven't
because I think in that case I think you'll get a spherical minimizer, right? For small s, you will not get a full dimensional minimizer.
Yeah, I haven't worked on that. But...
See, thank you. Any more questions? So.
I had a question from something that was a bit early on in the talk, but maybe it might have been something I misunderstood. So for carbon, you right. So for carbon, the n was equal to 6, and then you were saying the methods involved were generally for n beyond a certain value, which I forget what it was, but it was definitely something that was bigger than 6. Do some of the methods that you were talking about early on in the talk not work if you have very small n?
I mean, if you have small things, people can sometimes do better approximation for small n. For example, I said for n equal to, so you can work better with small n, but that's not very realistic. Yeah? It's not realistic to have just very few electrons in your system. Yeah? Sure. And the goal is to be able to say something for the large electrons. And then, yeah, so if you have smaller, little number, then things are a bit, you can do better math with them, so to speak. Yeah. But once you go to larger numbers, and yet the approximations don't work. So then they have DFT. I mean, DFT can be quite accurate they come up with these functionals, which I don't know where they come from. I mean, they can give you some physics motivation, which sometimes I cannot understand, but it makes sense to them.
Okay, thanks.
Let me ask a lyrical question. So you said that there was this conjectured constant of 1.4442.
Yeah.
So what is that? Is there any mathematical idea of what that is?
So let me. So this constant really is really what should. Let's go back. If I go back to this should be just this constant. Yeah. So this is what is. It should be CUEG. Should be 1.4442, and there's a lot of other conjectures that. I mean, it comes from trying to show in some sense that if I look at exchange correlation energy and divide by n to 1 plus s over d, it behaves in some way monotonically with respect to n. Yes, so then but it's not proved, it's just a conjecture. I mean, there are bounds. So what we have, there are bounds. So you have upper and lower bounds on this constant. Yes, so that there are bound on the CUEG, so you have some bound of 1.45, and the other bound was in the better one was 1.2 something. There are some bounds of, I can't remember, 2.9 I think is the other bound. I don't know what's the best lower bound now and currently. And but the upper one is 1.45, the best one known. So we can show some bounds for it. Yeah.
I see. Thank you.
And it evolved a lot over the years, what the best bound was. So they started with a bound between 7 something and 132, but then it got better and better. But you can't show 1.444 currently. We can show it. It will be awesome.
Thanks. Let's see. Are there any more questions on record, or shall we disable recording? Let's disable the recording. I have off the record questions about the weather and about